Hello there, Mr. Sutton here. I've got the AB Calculus Derivative Extra Practice number 10 solutions here. To take the derivative of this one, we have to realize that we have a variable in both the base and the exponent, so we need logarithmic differentiation on this one. I'll start by taking the ln of both sides. That's going to be ln of y on the left, and on the right, taking the ln pops out that tan of x as a coefficient, and then we have ln of the base secant of x. Next, I have to implicitly differentiate. So that's going to give me 1 over y dy over dx on the left side because y is being treated as an inner function, so we have to use the chain rule here. On the right side, we have a product rule with tan of x and ln of secant of x. So the derivative of tan of x, that's going to be secant squared of x. And derivative of ln of secant of x, that's going to be 1 over secant of x times the derivative of secant, which is secant tan. Now I'm going to multiply all this out using the ribbon. That's going to give me u prime v plus uv prime. So my first multiplication here, I've got secant squared of x times ln of secant of x. That's u prime v. uv prime is going to be going this other direction now, tan of x times all this stuff. Now I don't normally simplify if I don't have to, but I just can't help it here. These secants are going to cancel. Tan times tan is tan squared. But we still have to isolate dy over dx. So I'll multiply both sides by y to do that. That leaves me with a y times a parentheses with all this stuff in it. And if I just wanted to put this in terms of x, not necessary, but I could replace secant x tan x with the y down here. So there's another way of writing it. For this one, I'm going to need a product rule to take the derivative. So u prime v plus uv prime. Here's my box and ribbon to help with that. I've got factors of sine of 3x and ln of 3x. Derivative of sine of 3x, that's going to require the chain rule. So I've got sine of something. Derivative of that's going to be cosine of something, cosine of 3x. But I have to multiply by the derivative of 3x. So then in the end I have 3 cosine of 3x. Over here, same kind of idea. I have ln of something, derivative of that is 1 over something, 1 over 3x, but have to multiply by the derivative of 3x, which is still 3, hasn't changed in the last 10 seconds. Multiplying this out with the ribbon now, we have 3 cosine of 3x times ln of 3x, plus, and this is, I guess I could cancel these 3's if I wanted to, but I have sine of 3x and 1 over x then as the other term. For this problem, to take the derivative, I'm going to use the chain rule. My outer function, I've got cosecant of something. That derivative is going to be negative cosecant of something times cotan of something, the something being arctan in this case. Now I have to multiply by the derivative of the something, the derivative of arctan, which is going to be 1 over x squared plus 1. For this one, I have the log base 8 of e to the 3x, and I want to take the derivative of this. To make my life a whole lot easier, I'm going to pop out the 3x as a coefficient using my log rules. So let me rewrite this as 3x log base 8 of e. Now the really nice thing about this, although it's kind of hard to see at first, we have x, a variable, and everything that's being multiplied by x, they're all constants. We have a 3, we have a log base 8 of e. I don't know what that is numerically, but it's a constant. So whenever you have x times a constant, the derivative of that using the line rule is just the constant. So the derivative of this whole thing is just going to be 3 log base 8 of e. For this problem, I'm going to use the chain rule to take the derivative. My outer function, I have 3 to the something. That derivative is going to be 3 to the something times ln of 3. Now I have to take the derivative of the something, which was arcsecant of 3x. So that derivative, we're going to have 1 over the absolute value of 3x times the square root of 3x squared minus 1. But don't forget to multiply by the derivative of the 3x itself, the innermost function, and that's going to be a 3 out there. For this problem, before I go ahead and take the derivative, let me just rewrite this 3 over x to the 4th as a 3x to the negative 4. And now I'll do the derivative. I'm going to need the chain rule for this. My outer function is ln of something. Derivative of that is 1 over the something. And now I have to multiply by the derivative of 6 plus 3x to the negative 4. 6 is just going to be 0 when you take that derivative, But this next term here, using the power rule, we have negative 12x to the negative fifth. To take the derivative of this quotient, I am going to use none other than the quotient rule, u prime v minus uv prime over v squared. Let's set up the box and ribbon to help organize all that. So I have my numerator, e to the negative 3x. Denominator, which I'm going to rewrite as 3x to the fourth minus 2, all of it raised to the 1/5 power. Derivative of e to the negative 3x is e to the negative 3x times a tail of negative 3 using the chain rule. And then over here, this is going to be derivative of something to the 1/5 power. That's 1/5 times the something to the negative 4/5. But wait, now I have to multiply by the derivative of the something, which is going to be a derivative of 3x to the fourth is 12x cubed. Now putting it all together with the ribbon, I've got a big fraction, negative 3e to the negative 3x times this 1/5 term here. And then going the other way, we've got e to the negative 3x times all of this craziness. And down below, we've got this term here, this 3x to the fourth minus 2 to the 1/5 raised to the second power. So I could call that the 2/5 power, or I could just put the 1/5 inside and put the 2 outside. Doesn't really matter. We didn't have to simplify. On this problem, to take the derivative, I am going to need implicit differentiation because I can't isolate the y. So let me go left to right, and whenever I take the derivative of a y, I have to multiply by a tail of dy over dx, just using the chain rule, because y is an inner function at this point. So on the left side, I have a product rule to deal with. Let me use the box and ribbon to help with that. So we have 6x, and y squared is my two factors. Derivatives of those are going to be 6, and this is going to be 2y times dy over dx. There's that y tail, the derivative of y, because y is an inner function. Multiplying it out with the ribbon, we have 6y squared, plus this is going to be 12xy dy over dx. On the other side of the equation, 8x is going to become an 8, and this y is going to be a plus dy over dx. Now we're going to isolate the dy over dx's, so let me get those on the left side and get everything else on the right side. 12xy dy over dx, that can stay on the left. Let's subtract dy over dx to get it over there as well. And now I've got an 8 on the right side, and I'm going to join it with this 6y squared, which I'm going to subtract to get over there next to the 8. Now I can factor out a dy over dx from the left side, leaving me with 12xy minus 1. And to get dy over dx by itself, I'm just going to divide everything by this parentheses, put it down there underneath the 8 minus 6y squared, and call it a day. This problem, which we need to take the derivative of, looks like a huge mess. The good news is that since I've got some trig functions, I can try simplifying a little bit before I dive into that derivative, which would involve, let's see here, this would be a quotient rule with product rule on each side. Each of those is going to be a chain rule. Yeah, no thanks. This tan to the fourth of x, we can rewrite this as sine to the fourth over cosine to the fourth. And the good news about that is these cosines are going to cancel, leaving me with only sine to the fourth of x downstairs. But wait, there's more good news. We can cancel this sine to the fourth with this sine to the fourth. So that leaves us with only x plus 3 quantity cubed. So this is a little bit of a chain rule here, but not too bad compared to what we had before. This is something to the third power. So the derivative is going to be 3 times that something to the second power. So 3 parentheses x plus 3 squared. And then we have to multiply by the tail. But wait, the derivative of x plus 3 is just 1. So this does end up being our final answer. For this problem, this looks like a little bit of a mess to deal with, but we can actually simplify it first before taking the derivative. Both of these terms, I can factor a secant squared out of them. That would leave me with secant squared minus tan squared. And the reason this is good news is because these squared trig functions both appear in a Pythagorean identity. Tan squared plus 1 equals secant squared. Therefore, secant squared minus tan squared equals 1. Which means this whole thing inside here is really just 1, which is to say we can rewrite this as just secant squared of x. Now the derivative of secant squared of x, because we haven't actually done any calculus yet, we need to take the derivative. That's going to be, we have an outer function of something squared, so that's going to be 2 times the something, 2 times secant of x, times the derivative of secant of x, which is going to be secant of x tan of x. And this is a final, almost simplified answer. I guess you could write 2 secant squared of x times tan, but there's really no need. To make my life a little bit easier on this problem, I'm going to rewrite this second term as minus 3x to the negative third. Now I'm just going to go through and use the power rule. So this first one, this is going to be 24x to the fifth. And on this next one, we have positive 9x to the negative fourth.